So hello to whoever's watching this video right now. My name is Muhammad Reza, and today I will showcase our final code for our final assignment. So my task was mostly I was doing the documentation, the report of our group assignment. So let's get started. So obviously our first code will be importing pandas as PD, and then we obviously have to load the dataset. Our dataset accidental drug related death, and we display the basic information first. So df.info, it will show the information of our dataset, and then we can show the first 5 rows, which is df.head. The last 5 rows we can showcase as well, df.tail, and then we can convert date column to date time format. So this ensures that all the values in the date column are in proper date time format. And then the errors course, this to ensure that it converts invalid dates into NAT, not at time. And then we have the extract year from a date for trend analysis. In this code, we create like a new column, which is a year, and it only contains year, and it's extracted from the date column. Next we have our checking our missing values. So df.isNull.sum. So this shows like all the missing values in the dataset. And then after that we go to remove the duplicate rows. So df drop duplicates, any duplicate rows will be dropped. And after we drop the duplicates, we display the number of rows and columns. So the new number of rows and columns after dropping duplicate datas will be 11981 of rows and 49 columns. And then we will drop the specified columns. So these are the columns where we think it's not really necessary for the data set. So we see residence county, residence states, etc. And after we drop these columns, we will showcase the first 5 rows again. So df clean.head. And then moving on, we have our standardization standard scalar. So obviously if you want standard scalar, we have to import standard scalar from sklearn.preprocessing. And then from here we can select numerical features for standardization. So it indicates that this feature will only be standardized. So we will be using age, and then we have to initialize our standard scalar, which standardize features by removing the means and the scaling to the unit variance. And then we have our fit and transform the data, df clean numerical features equals scalar.fit transform. So obviously from the new clean data set that we did, we're going to include this, and fit transform, it basically it computes the mean and the standard deviation of age column, and it transforms them into a standardized format. Once we're done with all this, we will display the new scale data. So from the new scale data, we can see here that the age values in this table are now transformed into standardized values. So we see negative 0.553, negative 0.553. Yes, so it is now in a standardized value. So next we have our normalization minimum maximum scalar. So over here, obviously, if we want to use minimum maximum scalar, we obviously have to import it from sklearn.preprocessing. And yeah, so we used age column again for numerical features for the normalization. And then we have to initialize our min-max scalar so that we can create an instance. And again, we use the scalar.fit transform, where we can scale the age into the range of 0 to 1. And after we're done with all that, we can display the scale data. So from the scale data, we can see here from the difference between standard scalar and minimum maximum scalar is that this time it's not negative, and the age values are scaled between 0 and 1. This to ensure that the minimum maximum scalar is used to normalize numerical data to a fixed range, so it's between 0 and 1, and it ensures that all the values are proportionally adjusted while preserving relationships within the data. So next we have our problem 1, to determine which drugs cause most frequent accidental drug-related deaths. So in problem 1 we'll be using random forest and XGBoost. So over here we have binary encoding. So the binary encoding is applied to drug-related columns in this dataset. So we first group every drug into drug columns, and over here we have replace y with 1 and then with 0. Then we substitute y, which indicates like the existence of the drug, with 1, and all other values such as nan with 0. So yeah, the categorical data is transformed into numerical, and is to ensure that machine learning algorithms can use it. Next, we have our dfclean.head. So after we clean our dataset, we'll show the first 5 rows of our clean dataset. And then over here we have our imports. Import numpy as np. So this is used for numerical computations. So import matplotlib. So we use that for creating plots and visualizations. And seaborn as SNS. It's a statistical visualization on top of matplotlib that it provides better looking graphs basically. And then our machine learning libraries, we have a lot. So import train test split. So this is used for split data into training testing splits, and it's from sklearn model selection. Import random forest classifier from sklearn ensemble. It's a machine learning model based on decision trees. XGB classifier from XGBoost, plot importance from XGBoost. So for both of it, XGB classifier is used for optimized gradient boosting algorithm. The plot importance is a function to visualize the importance in an XGBoost model. And then we have our import accuracy score, classification report, confusion metrics from sklearn metrics. So yeah, all of this, for example, like confusion metrics, it creates confusion metric. It's basically like to show the graphs and the scores, the accuracy scores of our findings. And then import label encoder from sklearn.preprocessing. It encodes categorical labels into numerical values. And lastly, we have our import warnings. So the import warnings dot filter warnings. It suppresses warnings that might appear while running the code. So next we have our initialize and train random forest model, and with our predictions as well. So we have our performance metrics as well, where we will show our random forest accuracy and classification report. So over here is our classification report and our accuracy. So basically the model performs well. As we can see here, it's an accuracy of 99.79%, an F1 score of 1, which is right here, and basically it indicates that there's a near perfect prediction for the majority of classes. The weighted average stays at 1, suggesting that the model performs extraordinarily well overall. Despite the macro average, 0.86 precision here, 0.83 recall, and 0.84 F1 score, this suggests that a minor performance imbalance is between the classes. And then next we have our confusion metrics visualization, which is here, right here. So in this confusion metrics, this illustrates like how well the model performs across several classes. So the misclassifications are shown by off-diagonal values like this, and the actual predictions are represented by diagonal values. So more accurate classifications were shown by darker blue squares, like 765 for example. And then This basically correlates that it has a greater prediction count. The larger numbers such as 699 for class 3, 765 for class 8, and 653 for class 5. This indicates that the model performs well in these areas. There are a few small misclassifications that are visible, like the one that occurred for class 7. The model's accuracy is high since there are few instances of incorrect classifications, and the majority of values are clustered along the diagonal. So the 99.79% accuracy reported in the categorization report is also supported by this. So next we have our XGBoost model. So we initialize and train them with our predictions, and then we have our performance metrics for our accuracy and classification report. So in our XGBoost accuracy, the accuracy had 99.96%, and this is a perfect classification shown by the model's remarkable performance. The majority of the accuracy in the recall scores are at 1.00, and the underrepresented classes like class 7, which has a recall of 0.50. The class imbalance results in somewhat lower macro average scores. However, the weighted average accuracy stays at 1. So this indicates that the model is generally dependable. In comparison, the XGBoost model performs marginally better by 0.17% than the random forest network. And then we have our confusion metrics visualization here. And this will be our XGBoost confusion metrics visualization. Sorry. The confusion metrics for the XGBoost model, it's contrasted the model's predictions with the actual values. So the actual classifications are shown by the diagonal values, again like the random forest confusion metrics, where the greatest counts are represented by the deepest red boxes. So for example, like 765 here, it's a darker red color. So the highest classified instances, including 699 for class 3, 765 for class 8, and 653 for class 5, is similar to the random forest model. The great accuracy shown by the diagonal dominance supports the previously reported accuracy of 99.96%. So yeah, basically this excellent classification performance has low errors of XGBoost and is demonstrated by this confusion metrics right here. And next we have our random forest feature importance. So yes, this is our how we made the graph, plot figure, plot X label, plot Y label, same as like our confusion metrics here. So in this graph we have the random forest feature importance. So this emphasizes the drugs that have the most influence on the classification process. The y-axis displays the drugs, while the x-axis shows the importance score. So the heroin and cocaine have the greatest significance. This suggests that they have the most effects on the categorization result. Heroin, morphine, and codeine, fentanyl, and oxycodone, are other significant contributions. So this indicates that opioid-related drugs are important considerations in this analysis. And then we have this one, excuse me for mispronouncing this, and ethanol also exhibit significant importance, highlighting their function in drug-related instances. Even if they are less significant, the other characteristics such as methadone, hydrocodone, and amphetamines still influence the projections, and this determines which compounds are most pertinent to the dataset. This analysis aids in directing future research and intervention efforts. Well, next we have our XGBoost feature importance visualization. So In this visualization, this indicates which drugs have the most effects on categorization. The y-axis displays the characteristics connected to the drugs, while the x-axis shows the F-score. So in this visualization, this is a measure of how frequently each feature is utilized in decision trees. So any opioid is the most important with the F-score of 754. This is followed by heroin, morph, codeine with a F-score of 203. And then we have benzodiazepine with a F-score of 307. And then fentanyl with a F-score of 208. And there's other drugs such as gabapentin, oxycodone, and cocaine. Excuse me if I mispronounce it. So they also have a role, but it's less significant than the ones we just mentioned.
Hi, my name is Akira and I handle the coding part and some of the report. So today I'm going to discuss about problem 2 to determine which age group are at high risk for drug overdose death. So we're going to implement this using elbow method and silhouette score to find the optimal K for our K-means clustering. So first of all, we need to import important libraries such as K-means, standard scalar, and silhouette score. Okay, next, we're gonna standardize our age by using standard scalar. And once we standardize the age, we remove the rows that have missing value in age column and fit them into the data. And next, we're gonna use the elbow method to find the optimal K. So first of all, we need to create a list for inertia and silhouette score. And for the range, we're gonna put 2 to 10 for the K values. And once we're done setting the range, we're gonna create a K-means model with K clusters and a fixed random state for reproducibility. Next, we're gonna use K-means fit to train the K-means model using the H scale dataset. And once we're done with that, we're gonna use inertia append to store the inertia and silhouette score append to compute and store the silhouette score. Once we're done with configuration of the elbow method, we can plot out the elbow method. So this is shown in this graph where the y-axis is the inertia and the x-axis is number of clusters. The elbow method plot visualizes the inertia. The goal is to identify the optimal K value where adding more cluster results in minimal improvement. The graph shows a sharp decline in inertia from K equals to 2 to K equals to 4, followed by a more gradual decrease. The elbow appears around K4, indicating that this is the optimal number of clusters, as beyond this point the reduction in inertia is minimal, suggesting that diminishing returns in clustering effectiveness. So these are plots for our elbow method for the optimal K, and this illustrates the correlation between the inertia and the number of clusters. For better clustering is indicated by a decrease in inertia as K rises. However, the pace of decline slows down and forms an elbow here, as you can see. The elbow in this figure develops at K equals to 3, indicating that 3 clusters offer the best choice between avoiding excessive complexity and minimizing inertia. This decision guarantees significant grouping without causing the data to become overfit. Okay, once we're done plotting the elbow method, we need to print out the inertia scores. So here's all the 8 inertia scores, as you can see. It goes from 3,284 to a number of 232. Once we're done with elbow method, we're going to continue with a silhouette score by plotting out the graph. So as you can see from here, The silhouette score analysis shows how distinct the clusters are for a range of k values in the visualization. Clusters' cohesiveness and separation are measured by the silhouette score, and better defined clusters are indicated by a higher value. Based on the graph, the silhouette score peaks at k equals to 2, which is around 0.62, and subsequently it falls as k rises. The score is still high between 0.55 for cluster 3, indicating a strong balance between separation and cohesiveness. The silhouette score keeps decreasing beyond 3, suggesting that grouping becomes less recognizable as the number of clusters increases. So this proves that k equals to 3 is the ideal clustering value for our k-means clustering. Next, after we're done with plotting the silhouette score, we need to print out the average silhouette score for average clusters. So first of all, we need to put the range in between 2 to 10, and once we put in the range, we can create a k-means clustering model with I clusters, and random state 42 is used to ensure that the results are reproducible. And next, we're gonna fit our k-means with each scale variables. And once we're done with that, we're gonna use silhouette average and silhouette score to calculate the silhouette score, which measure how well each data point fits within its assigned clusters compared to other clusters. If the value is closer to 1, it indicates that the data point is well clustered, and if the value is closer to -1, it indicates that the data point might be assigned to the wrong clusters. And if the value are around 0, it indicates an overlapping of clusters. So from the print clusters, we can view that the first cluster is 0.61, which is it's close to the value of 1, where it indicates that the data point is well clustered, and it goes on and on with the other clusters. Next, after calculating the average silhouette score, we need to choose the optimal k, which is equal to 3. And after setting the k value, we need to train our k-means model. We're gonna train the k-means with a random state of 42 for reproducibility, and each data point is assigned to a cluster label stored in the H cluster. After training the cluster centroids are transformed back to the original scale using scalar inverse transform to reveal 3 representative H group. Which is 30.52, 46.08, 59.94 years. These centroids represent the central point of each cluster, helping us to interpret the segmentation of each group better. Okay, next, once we're done with getting the centroids, we need to add the H clusters back to the original data frame. So next, we need to assign labels, which will be in the variable called H categories. The 0 will represent young adults, the 1 will represent older adults, and 2 will represent seniors. Following the addition of this categorized age group, the value .counts function is used to count the number of occurrence deaths inside each category. On the output here, you can see that the young adults has the greatest count of a 4,069 of death, while older adults have a 4,281. Meanwhile, for seniors, we have a value of 3,229. So the reason why we did this is to aid us in comprehending and how fatalities are distributed throughout various age groups. Okay, next, after we're done assigning labels for 3 of the centroids, we need to plot out the visualization using pie chart. So based on the pie chart, we can see that the value of 37.3% of the total represent a young adults, which make up the highest percentage among all three of them, followed by older adults with the value of 35.7 and seniors with the value of 27%. This is obvious for us that we can see young adults have the highest risk to a overdose death, which we can focus more when it comes to overdose prevention initiative. Okay, next, we're gonna need to plot the scatter plot to visualize the distribution of the individual across three age group, which are young adults, represented by the red dots, and older adults, represented by the blue dots, and seniors, represented by the green dots. So, for young adults, we can see it was grouped between 18 years old to a 36 years old, around there, and older adults we have around 36 to 55, roughly around there, and for seniors we have around 56 of age and above. So from there we can clearly see young adults to be at the most danger because the clustering, the distribution of young adults is denser and is more concentrated, indicating that there are more individuals on this group. Like you can see this huge piece is bigger than the blue dots and the green dots. Okay, next we're done with our problem 2. So we're gonna go to problem 3, which is to determine the overdose death over the years by using linear regression and polynomial regression. So first of all, of course, we need to import important library. For training linear regression, we need to import linear regression, polynomial features, and to count the matrices, we need to do count A. Okay, we're done with our problem 2. So let's dive into problem 3, which is to determine the overdose death over the years by using linear regression and polynomial regression. First of all, we need to import important libraries such as linear regression, polynomial features, mean absolute error, mean squared error, and R-squared score. After we're done with importing the libraries, we need to define x and y. So for our x, we have the year column. For the y, we have the total drugs. After defining x and y, we'll need to split them into training and testing sets of 80 to 20, which the test size is 0.2, which is 20% for the testing, and 80% is for the training. Next, after we're done with training the using linear okay, next, after splitting the dataset into 20% of testing, we need to training using linear regression by first initialize and train the model of linear regression, and then we fit it into X train and Y train. And after we train the model, we can make prediction by using the model predict X train and model predict X test. Okay, here is where we do the performance matrices. So first of all, for linear regression, we can calculate the performance matrix of MAE, MSE, RMSE, and R squared. I added an extra of adjusted R squared calculation to see like if we can get any better results. And once we're done with that, we can print all the results of the matrices. So as you can see from here, for our MAE, we have the value of 1.10, and MSE, we have the value of 1.93, and for our RMSE, we have the value of 1.39. As for our R squared, we have the value of 0.09, and for the adjusted R squared, we have a better performed result of a 0.0871. Okay, next, after we're done with calculating the performance metrics for linear regression, we need to plot out the visualization. Okay, so here we have our overdose death over the years visualization using linear regression. So for the blue dots, it represents actual death, and for the red line is the regression line. So the y-axis is total overdose death, and year is on the y-axis, which is in between 2012 to 2023. So as you can see from the graph, the highest value recorded for actual death is actually the year of 2023, the value of 10. And for the regression line, it suggests a slight upward trend in overdose death over time. This implies that a gradual increase in fatalities over the years. We are gonna train the problem 3 with polynomial regression by using the degree of. Okay, next we're gonna train using polynomial regression. First of all, we need to choose a degree of the polynomial which is equal to 4, and after that we transform the input features using the xtrain and xtest into a polynomial features. Then the transform data is then used to train linear regression, and it is fit into it. Once we train the polynomial regression, we can make prediction using xtrain polynomial and xtest polynomial. Okay, next, once we're done with training the model and making prediction from it, we need to calculate the performance metrics for polynomial regression, such as MAE, MSE, RMSE, and R squared. And as I mentioned previously, I'm going to use adjusted R squared to see like if we can improve the R squared value. So once we're done, we can print out the results. So from here, we can see that the MAE have the value of 1.08, MSE we have the value of 1.84, RMSE we have the value of 1.35, and the R squared we have the value of 0.1330, and the adjusted R squared is 0.1312. Okay, so once we're done with calculating the performance metrics for polynomial regression, we need to plot out the prediction. So here is the visualization for our polynomial regression, and as you can see, the blue dots represent the actual death and the red curved line represent the polynomial regression with the degree of 4. Okay, so unlike linear regression, which fits a straight line, polynomial regression captures nonlinear trends, making it more suitable for dataset with fluctuations. So from the curve, we can conclude that the overdose death initially increases over time, but it shows a sign of stabilizing or slight declining towards the later year. So this can indicate that while overdose death followed a rising trend initially, but the rate of increase may have slowed down or reversed. So we can conclude that polynomial regression provide a better prediction over the years compared to linear regression. Okay, next, to conclude our analysis, we will be discussing 3 problems that we managed to achieve, which problem 1, we managed to determine which drug caused the most frequent accidental drug-related death. So for random forest, we have the result of cocaine and heroin. And for XGBoost, we have the result of any opioid-related and benzodiazepine. As for problem 2, we managed to solve that which age group are at high risk for drug overdose death, which came to a conclusion that young adults, which achieved the percentage of 37.3% among 3 of the group clusters, and they aged between 18 and 36 years old. For linear regression, we able to conclude that it shows a slight upward trend along the years between 2012 to 2023, which is the linear regression line. And for polynomial regression, the curved regression line, it increased over time, but is slightly declining from the year of 2018. Thank you. That's all for our video presentation, and hope you like it.